Hey mathletes, what's up? It's Mr. Nolde here. Today, going to talk to you about more advanced transformations. Specifically, they are called non-rigid transformations. Previously, we looked at rigid transformations. Today, we're going to step it up a notch. All right, so previously we were talking about what I call basic transformations. They're called rigid transformations. In that, the only thing we're doing is moving the figure left and right, up and down, or possibly, reflecting it on the axis. So it looks something like this. A reflection. But notice in no instance does the figure change. The figure remains intact. The figure's the same, it's just that we've translated it or rotated it. So an example of a non-rigid transformation rather than a rigid is one that changes the shape of the figure. So for instance, we could have our figure like this, and instead of up and down, which is a translation or a rigid transformation, we could be shrinking this figure like this, shrinking it this way, or shrinking it or stretching it vertically. Or you could do both at the same time. So this is kind of what we're talking about today with the non-rigid transformations. We're actually changing the shape of the figure on the XY plane. Okay, so an easy way to start this is to look at the parent function that I have pictured here. It is the function y equals the absolute value of x, which we know graphs like this, like a letter V. But suppose I wanted to stretch that. If I wanted to stretch that vertically, I would have to multiply it by some number on the outside bigger than 1. Let me go ahead and select here. I'm going to move this out of the way. So I'm going to change this to, say, y equals 2 times the absolute value of x. So now what we're doing is we're taking this absolute value of x function value and we're increasing it by a factor of 2. So it would graph something like this. It's a rough sketch, but you get the idea. So what's happening is this yellow function is being stretched vertically. So outside of the function is going to stretch it vertically, and this number is bigger than 2. Now, suppose I had a number here that was less than 2. Right? Suppose I had y equals 1/2 of the absolute value of x. Now it's going to take my red function values and cut them in half. So it may look something like this. So here's the green function. So this happens when I'm multiplying on the outside. When I say the outside, I mean outside these absolute value symbols by a number less than 1. A number greater than 1 is going to stretch it vertically. So I'm going to pencil that in here. This is called a vertical stretch. And we would say it's a vertical stretch by a factor of 2. So a factor of 2. And the different books call it different things. Like this green function could be called a shrink. It's like you're compressing it this way on the x-axis or on the y-axis. So sometimes it's called a shrink, but it's still technically a stretch. But it's by a factor of 1/2. So stretch by a factor of 1/2. 1/2. And that is essentially what a vertical stretch is. So in the next slide, I will show you a horizontal stretch or a horizontal shrinking. So it is important to note that oftentimes a horizontal shrink can look like a vertical stretch. So if I were to multiply the inside of this thing, let's suppose let me go down one little section, and I'm going to start with y equals x plus 2 the quantity squared. So this tells me, this plus 2, that I'm going to take the parent function that was right here and move it to the left by 2 units. So I'm like, okay, here's the parent function. So I'll write parent next to that. Then we're going to go 2 units to the left. So this is what we talked about with transformations. So the shape of this curve has not changed whatsoever. We've just moved it over. But now we're going to take and multiply the inside by a number greater than 1. Say 2. So what's going to happen is that is going to shrink it in the horizontal direction. So it's going to end up looking like this when it gets shrunk in. So that looks very much like a horizontal, the horizontal shrink looks very much like a vertical stretch. So the thing to remember is that big numbers make things squish in or spread out. So if you think of it that way, the big numbers make things squish in or stretch out horizontally. So stretch out horizontally or squish in. I'm sorry, just misspoke. Stretch out vertically or shrink in horizontally. So those are our big numbers. So let's look at the next slide here, which deals with a smaller number. So here's one that has a smaller number. Notice this is not on the outside, it's on the inside. So this is going to spread this function out this way. So it's a smaller number. So a spreading horizontally is similar to a shrinking vertically. So when you have small numbers. So we're going to take x plus 2, quantity squared, but we're multiplying this x by a half. So I'm going to write first what the parent function would be shifted to the right. It would look something like this. But then we're going to multiply the x by a half, which is going to spread it out thusly. So, not a perfect sketch, but it'll give you the right idea. In yellow, it's going to be kind of laying out flat like this. So that's kind of like multiplying this by a half, which is on the outside. So on the inside, it does the same thing. It's going to have the same effect. It's either going to shrink it vertically or stretch it horizontally. So that's the way to keep track of the numbers bigger than 1 and the numbers less than 1. The bottom line is we've got to do these again and again and again in our assignments. So we'll look at one more quick example. Okay, so here's a function that will combine a couple of the things that we've just been talking about. Notice it's also going to be combining some of the rigid transformations. So this is just going to move stuff left and right. It's going to move it 1 unit to the left, 4 units down. But on the outside, not on the inside, this is going to shrink it vertically by a factor of 1/2. And then it's also going to be flipped over the x-axis. So let's label my x-axis and my y-axis. So I always like to start with the parent function, which looks like this. So this is my parent function, y equals the absolute value of x. And maybe I'll switch up some colors here now. I'm going to move it 1 unit to the right. So it's going to end up looking like this when it gets moved 1 unit to the right. Then I'm going to move it, I'm going to flip it. I'll flip it. How about that? So then it gets flipped like this. Then it will get, let me pick a different color here. It will get stretched by a factor of 1/2. So it's being vertically stretched. Okay, this is a vertical stretch. It looks like it could be a horizontal stretch, but a vertical shrink and a horizontal stress. I'll use shrink so you understand better that I'm talking about up and down movement. So that is a vertical shrink by a factor of 1/2. Then the last thing that gets done to this guy is, let's see, he gets moved 1 unit, not 1 unit, 4 units down. Let's see, I like this color better. How about 4 units down? So 1, 2, 3, 4. So that would put it about like this. So this is parallel to the purple one. This is parallel to purple. Because we shrunk it by 1/2 on the purple step, the blue step here, we're just moving it down 4 units. So this is the final piece right here. So I'll draw that around and have it go up there. So that was a lot. If you've been doing your readings and doing your homeworks and practices, hopefully this is just a fast recap. If you need more than this, then check back in later and I could give some better lessons that start from the very beginning. Okay, superlative job as always. That was a little bit more tricky than the rigid transformations, but you're smart. I'm pretty sure you're going to get it. If you want something a little bit more basic, please be sure to include it in the comments down below, and I will make another video. In the meantime, remember that you have to do math to get good at math. Math is not a spectator sport. So until next time, sports fans, it's Mr. Noldy.